The title of this presentation is Robust Scheduling of the remanufacturing process for the repair of turbine blades. Gas turbine is one of the most efficient power generation plants in the world, and there are several leading manufacturers like GE, Siemens, and others. The global gas turbine market size is very large and is still increasing. Gas turbine blade is one of the most important parts inside the gas turbine, and the price of the turbine blade is really expensive. A single blade equals about 10,000 euros. And the life cycle of a gas turbine is about 25,000 hours. After this, the blade needs to be disassembled and maintained. But due to the high value, the power plants often require the refurbished blades. So we can see that this match the typical characteristic of remanufacturing and circular economy business model. Now I'll introduce the remanufacturing process of turbine blades. The blades are always processed in batches. All the batches need to go through disassembly, inspection, remanufacturing, reassembly, and then deliver back to the power plant. Here in this project, we focus mainly on the remanufacturing part, and I listed several key activities of this process, such as defect removal, laser welding, grounding, and non-destructive testing. Specifically, for the laser welding and grounding activities, blades quite always need to be reworked by repeating these two operations, requiring the same resources. Okay, now let's see what's the problem in this process. The repair process is affected by a significant degree of uncertainty. Firstly, the blades entering the process with different wear states, and the repairing time could be different for each blade. And also, the blades with heavy damage could not be repaired. So some blades in the batch are discarded and substituted with the new ones. This will lead to the uncertain number of blades in the repair batch. Grounding on these two factors, the processing time of each batch of blades is uncertain. And from the historical data, we can see that it cannot be described by the classical distribution. Okay, now I'll summary the problem. We consider the subset of bottleneck resources in the remanufacturing process, the laser welding and grounding phases, which can be modeled as a two-machine flow shop. The processing time of each batch of blades can be described by the stochastic distribution. All the batches need to be reworked by repeating the same sequence of operations on these two machines. And the objective function is to maximize the utilization of the resources. Hence, the mixed ban on these two machines are considered. And a robust scheduling approach is needed to mitigate the impact of uncertainty. Specifically, the value at risk approach is exploited in this project. Okay, firstly, I'll introduce the value at risk. Value at risk is one of the risk measures, and it can estimate the stochastic feature than the expected objective function, and is less conservative than the min-max approach. Originally, it stems from the financial optimization area and now also popular in the scheduling field. To use value at risk, we need to describe the uncertainties associated to the processing time and then derive the distribution of the objective function and calculate the VR value. Once we have a VR value of the schedule, we can see within a specified risk level alpha, we can see the maximum objective function we can experience is the best 1 minus alpha percentage of the scenario. Or we can see the 1 minus alpha level confidence that the objective function will not exceed the VR value. Okay, now I'll give the solution framework. the two-machine flow shop can be described by the activity network, but due to the stochastic processing times, the critical path may be various and dependent. And also, we want to model the processing time distributions of the real industrial plant. So we exploit the phase type distribution. Grounding on these two, we can calculate the distribution of the objective function with an innovative Markov activity network, and then calculate the VR value with the root finding method. This is an evaluation of a single schedule. We developed the branch and bound algorithm to find the optimal schedule, minimizing the VR value. This is the solution framework of this project. Okay, then I'll give some details about the branch and bound algorithm. For the leaf node evaluation, the network, we use the activity on arc network, and the rework activities are modeled as the additional jobs. The rework job for sure should be scheduled after the processing of the general job. Okay. And from the theory of Markov activity network, at a given time, an activity can only be in active, dormant, or idle, one of these states. So we can automatically generate all the possible states. And from the first state until the observed state is the mixed span of the network. This is finally in a continuous time Markov chain. Okay, then we can evaluate the distribution from the infinitesimal matrix of this Markov chain. Okay, for the non-leaf nodes, we must be able to evaluate the partial schedules. Okay, firstly, we sum the unassigned jobs on machine A and machine B respectively as KA and KD, and also we relax the precedence relations between KA and KD. Okay, and also due to the VR or the mixed span is a regular objective function, so these can be proved to be in the lower bound. And also the continuous time Markov chain generation scheme can be also used here to estimate the lower bound of the VR value. This lower bound of VR will guide the search in the branch process and cut the branches without possibility finding the optimal schedule. We tested our algorithms in a real case study, which is in the case from the Ansaldo Energy, which is the gas turbine blade manufacturer located in Italy. And we used the phase type distributions to fit the historical data of the processing time within 10 to 15 phases. It gives good results. And also, we tested the algorithm on the scheduling horizon of 3 to 6 months. Okay. We can decrease the mixed band value from 5 to 8%, and within half an hour computation time. Okay, this demonstrates the efficiency of the proposed algorithm. Okay, now I'll conclude this project. A branch and bound algorithm is developed to schedule the remanufacturing activities for gas turbine blades, pursuing the robustness by minimizing the value at risk of the mixed span. The approach demonstrated good performance on the industrial scheduling instances, and the further developments will address the different scheduling problems and the improvement of the computational efficiency. Okay, that's all. Thank you.